Lesson 4, Standard Enthalpy Change of Formation. So in this lesson, we're going to continue on with the idea of Hess's law using something called standard enthalpy change of formation given by the symbol delta H sub F. So this is the enthalpy change that occurs when 1 mole of a substance is formed from its elements in their standard states. These standard measurements are taken at a temperature of 298 Kelvin and a pressure of 1.0 times 10 to the 5th pascals. They are important as they give a measure of the stability of a substance relative to its elements, and it can be used to calculate the enthalpy change of all reactions, either hypothetical or real. So let's start with an easy question. The enthalpy of formation of ethanol is given in section 12 of the IB data booklet. Give the thermochemical equation which represents the standard enthalpy of formation of ethanol. So when you see the word formation, you're going to try to make your substance and make exactly 1 mole of that substance from its elements. So if you were to go to the data booklet and you would look up ethanol, you would see that it has an enthalpy change of negative 278 kilojoules per mole. Now, ethanol, which is given by the formula C2H5OH, is made from the elements carbon, hydrogen, and oxygen. Now, the thing to remember is they need to be in their standard state. So, carbon is given as graphite, hydrogen is listed as H2 because it's diatomic and it's a gas. Same for oxygen. So we write the equation for carbon plus hydrogen plus oxygen gets us to our ethanol. Next step is to make sure it is balanced. Now, because the enthalpy change of formation refers to 1 mole of a product, there are fractional coefficients in the balanced equation. Okay, so you'll see that with the oxygen, because there is only 1 oxygen in ethanol as your product, you only need a half of an oxygen molecule. So we could just plug in our delta H from the data booklet, negative 278 kilojoules per mole, and this is the enthalpy change of formation of ethanol from its elements. Okay, let's try a couple of practice questions. Which of the following, in number 21, does not have a standard heat of formation value of 0 at 25 degrees Celsius and 1.00 times 10 to the 5th pascals? Okay, so you can see does not have a standard heat of formation value of 0. Well, one of the things to note is that every element must be in its standard state. So a question like this is asking which element is not in its standard state. An element in its standard state will have a heat of formation value of 0. An element not in its standard state will have a different number. Okay. Chlorine, let's look at our examples. Chlorine is a gas at room temperature. That is true. That is its standard state. Iodine is a solid. That is also true. It is a solid in its standard state. Bromine as a gas, that is not true. Bromine is a liquid in its standard state. And then just to double check, sodium is a metal, which means it is a solid, which means letter C, bromine gas is not its standard state. Number 22, which of the following does have a standard heat of formation value of 0 at 25 degrees Celsius? So, just like before, we're looking for the element which has a standard heat of formation value of 0, which means the element is going to be in its standard state. Well, let's look at our examples here. We have hydrogen and A, but we know that hydrogen is diatomic, therefore it should be H2, so that is not. Mercury as a solid, well, that is not true because mercury is a liquid. C is carbon listed as diamond. Well, from the slide before, we know that the standard state of carbon is graphite, so that is not true. And silicon as a solid, that would lead us to our correct answer. That is the element that is in its standard state and therefore will have a heat of formation of 0. Okay, let's look at number 23. For which equation is the enthalpy change described as an enthalpy change of formation? So here we have to use the definition of enthalpy change of formation from before, making 1 mole of a substance from its elements in their standard state. So take a look at all those examples first. Well, if we look at our first letter A, we're making 2 products. So that's not true because we need to make 1 product. Letter B, we are making 1 mole of our product, so that is true. Now we have to consider, is aqueous the standard state? Okay, well, let's hold off to that because that might be true. Letter C, we are making 1 product, but it is a hydrated product. Okay, that might also be true, so we'll hold off on that. And letter D, again, we're making that copper 2 sulfate, just like in letter B, but now it's in a solid versus its aqueous form. Okay, well, if we look quick at letter C, we're making our product, but it's not forming from its elements. So C is not the correct answer. So that leaves us with B and D. Both of the elements and the reactants are the same. So now we have to consider our product. Well, the standard state of copper 2 sulfate is a solid and not aqueous. So that would lead us to believe that D is the correct answer. Okay, so enthalpy change of formation, the elements in their standard state come together to form 1 mole of a product. Let's look at number 24. Write the thermochemical equation for the standard enthalpy of formation of propanone, CH3COCH3. And then in letter B, state the conditions under which standard enthalpy changes are measured. Okay, so we need the thermochemical equation, which means we're going to need the elements that are used to make propanone as well as the delta H, okay, which we can find in section 12 of the data booklet. Okay, well, very, very similar to ethanol, you have carbon, hydrogen, and oxygen. So write those in their standard states and then balance the equation. And then look in table 12 for the enthalpy change, and you should get something like this, where you have 3 carbons plus 3 hydrogen molecules plus a half of an oxygen molecule gets us to our propanone, and then delta H is given as negative 248 kilojoules per mole. So the elements come together to form 1 mole of propanone. And then it says for letter B, state the conditions under which standard enthalpy changes are measured. Okay, well, if you remember from before, 298 Kelvin, 25 degrees Celsius, and then 1 times 10 to the 5th pascals. Okay, something else to note is that if the reaction involves solutions, these have a concentration of 1 molar. So how does all of this come together? Well, standard enthalpy changes of formation can be used to calculate the standard enthalpy change of any reaction. Okay, so let's consider what this chart is showing us, and it's very similar to the Hess's law chart that you saw in the previous lesson. So at the bottom, you see the elements. Okay, these could be any elements. Okay, but we have to remember that the elements are in their standard state. Well, those elements can be combined in two different ways. One way, it could be used to form reactants. The other way is to take those elements and form products. So this is why you see two delta H's. One is used to make the reactants and one is used to make the products. Now what happens is those reactants react together to form the products. And this is where you see the delta H of the reaction. This is what we're trying to find. So we can take the elements, look at the delta H sub F, the enthalpy of formation of the reactants, the enthalpy of formation of the products, and we can put this together to calculate delta H of the reaction, or the enthalpy change of the reaction. So if you remember from Hess's law, it doesn't matter which direction you go, how you get there, the change is going to be the same. So from the elements, you could see that there are two colors, blue and red. So to get to the products, we have two possible pathways. Okay, we can start with the elements and go directly to the products, and this is the sum, that's sigma, meaning the sum of the delta H sub F, enthalpy change of formation of the products. The other route that we can go is we can take those elements to form our reactants, and we could sum up the delta H sub F, or the enthalpy change of formation of the reactants, and then we add that to the enthalpy change of the reaction to get to our products. So we have the red pathway and the blue pathway. Well, it doesn't matter, they're going to be equal, which is what we have from our diagram. If you look at the first line, you add the two red arrows together, and that's going to equal whatever this blue arrow was. Well, the ultimate purpose is to try and find delta H of the reaction. So we can just do a little subtraction to get this final equation down at the bottom that you need to remember. So the delta H of the reaction can be found by summing up the enthalpy of formation of your products minus the sum of the enthalpy change of the reactants. Okay, this is the equation that you need to learn. It is not given in the data booklet. All right, let's look at an example together. So a common question that you could be asked is calculate the enthalpy change for the reaction from the following standard enthalpy changes of formation. So one way a question could be asked is to calculate the enthalpy change and then give you a data table with the substances listed as well as their enthalpy of formations, like we're doing in this problem. Now you will notice that the equation has 4 substances listed, but only 3 are included in our table. You will notice that oxygen is not given. That is because it is an element and it has a delta H of formation of 0. Any element in its standard state has a delta H sub F of 0. So in problems like this, you ignore any elements in their standard state and just give it a value of 0. Okay, you have all the other delta H sub F's for the other substances, the other 3 substances listed in the equation. So first, you're going to write the balanced equation with the enthalpies of formation. Now, one thing to note is that these are stoichiometric relationships. What that means is if there is a coefficient, you need to take that into account and multiply the enthalpy of formation. The enthalpy of formation is given for 1 mole. So if you have 2 or 3 or 4, as we see in our example, you need to multiply that value by whatever the coefficient is. So you see the values are given for the reactants, negative 105, all the way to the left. You have the 0 for the oxygen. You have negative 394 for the carbon dioxide. and we're going to multiply it by 3 because there are 3 carbon dioxides. And then we have negative 286 for the water, and we're going to multiply it by 4 because there are 4 waters. Since delta H of the reaction equals the sum of the products minus the sum of the reactants, we simply add up and then subtract. So we're going to take our right-hand side because those are our products. We do 4 times negative 286 plus 3 times negative 394. And then we're going to subtract 0 plus a negative 105. Okay, you can see that there are brackets around the products, the left-hand side here, and there are brackets around the sum of the reactants, the right-hand side here. That's very important because you have to sum up the inside and then you subtract, do products minus reactants. So when we do all that, we get negative 2,221 kilojoules per mole. Okay, so delta H of the reaction equals the sum of the products minus the sum of the reactants. Okay, why don't we do some of these problems, try them first on your own, and then you can compare them to the answers that are going to be given. Okay, here's a question very similar to the previous one. You're given a balanced chemical equation. It's already balanced for you, and you have to calculate delta H in kilojoules per mole based on the following data. So you look at your products, you look at your reactants, you'll notice that there are 2 elements listed in your equation, carbon and iron, and they are given a value of 0. So if you do this correctly and do sum of the products minus sum of the reactants, you should get a value at the end of positive 330 kilojoules per mole. All right, one thing to note is it is listed as a positive. Okay, start to get used to writing that. Even though the answer is positive, you have to write the positive symbol. Okay, again, try this equation, this problem on your own. Again, the answer will be given to you. You may want to pause the video and try it on your own first before you check the answer. Okay, this one, there's only 2 substances in the equation and only 2 substances in the data below. Pay attention to the coefficients, sum the products minus sum of the reactants, and you should get an answer of negative 57.2. So before the answer was positive, that was an endothermic reaction. Here we have a negative as our enthalpy change, so this would be an example of the exothermic, okay, the negative symbol, negative sign. Okay, here's a multiple choice question that you can try to answer. Okay, try it on your own, pause the video if necessary. Sum of the products minus sum of the reactants. Again, no oxygen is listed because it is an element. You cannot form an element from its elements. It's already in the elemental state. Okay, if you do this correctly, you should get D as your answer. And here is the work if you want to check it out. Okay, we have one more problem here. Number 28, you're going to calculate the enthalpy change for the hypothetical reduction of magnesium oxide by carbon according to the equation below. Comment on its feasibility. Okay, so why don't you do the first part first, the math. Okay, you're only given the data for the 2 compounds that are given in the equation. Okay, hopefully you remember what the formula that you need to use to calculate the enthalpy change. Okay, sum of the products minus sum of the reactants. You remember the coefficients, take those into account. And then comment on its feasibility, meaning, is this reaction going to actually occur, or is it more of a hypothetical question or hypothetical equation? Well, if you do the math correctly, you should get positive 810 kilojoules per mole, which is a really, really endothermic reaction. And because it is so endothermic, which means you are adding energy and the products are going to have higher energy than the reactants, it is unlikely to occur and therefore is unlikely to be feasible. And as is noted, instead, magnesium is produced by electrolysis of its ores, which we will learn what that means at a later date.